Hello and welcome into the content video for lesson 13 for Precalculus 1. In this video, we're going to be looking at inverses of functions. And so what this is doing is essentially giving us the reverse version of the function. When we started talking about functions, I gave you guys the example of a salary that if you're making $10 an hour and if you work 5 hours, you make $50. Now we're going to kind of do the reverse. Excuse me. So if you're making $10 an hour and I told you, oh, you made $50, you could figure out, okay, based on the function, based on the outcome, what would the input be in that case? 5. But with inverse functions, let me share my document camera here. So the thing about inverse functions is, or what I should say is a function can only have an inverse if it's 1-to-1, meaning that your output can only be derived from one given input. So for example, if I told you, oh, you made $50, it couldn't be that you worked 5 hours or it couldn't be that you worked 10 hours. It has to just be one specific value. And so again, we call that 1-to-1. So our definition of a 1-to-1 function is that a function with domain A is called 1-to-1 if no two elements of A have the same output. So what that means in terms of our function is if I have some value x1, f of x1 cannot be, excuse me, the same as f of x2 if x1 is not equal to x2. So again, if we use our salary example, if I work 10 hours and I make $120, that's it. There's no other amount of time I can work that's going to give me $120. And so graphically, we can see this using what's called the horizontal line test. We have that a function is 1-to-1 if and only if no horizontal line intersects the graph more than once. Whoops, sorry, let me move that up for you. So horizontal line test, the function is 1-to-1 if and only if no horizontal line intersects the graph more than once. And so the most famous example we have, or the most common that we know right now, is what? Our parabola, right? So if f of x is equal to x squared, well, this is obviously not 1-to-1 because pretty much anywhere I draw a horizontal line, it's going to hit this graph at 2 points. So we can have x squared as long as we put domain restriction, because if, for example, if I said, let's say g of x is x squared, but x is greater than or equal to 0 only. Well, then that graph would look like what? It would be starting down here in the vertex and just the right half of the graph. And in that case, that is 1-to-1 because any horizontal line is only hitting this graph once. So using domain restrictions, we can create 1-to-1 functions. A property of the inverse function property. Oh, you know what? I should first, let me give you the definition so we know what our terminology is that we're talking about here. So definition of the inverse function. So let f be 1-to-1 with domain A and range B its inverse function and we write this with like a little -1 up at the top. So this means f inverse. So not f to the -1 power, just f inverse. So its inverse function, f inverse, has domain B and range A. So if I know that, let's say the range of my my base function is 0 to infinity, then if I ask you guys like, okay, well then what's the domain of the inverse function? Well, if the range of the regular function is 0 infinity, then that means the domain of the inverse is 0 to infinity. Don't complicate it. So if f has domain A and range B, then f inverse has domain B and range A. They just switch. That's it. And vice versa as well. You could go if you know the inverse. So that's going to come in handy in 126. It's going to come in handy in 127, especially. Okay, now that we've kind of defined our inverse function and its notation, then we have the inverse function property. We have the following f of f inverse of x is equal to x. So if I take the inverse function, I plug it into f, and then simplify. If I end up with just x, then I know that these two are inverses of each other. So if I'm given two functions and the question is, are these guys inverses of each other? That's how I can test. Just plug one into the other, and if I get x as my final answer, then the answer is yes. And similarly, f inverse of f of x is also equal to x. Excuse me here. So if we're given a function, how do we find the inverse function? Well, we do that with the following steps. So to find f inverse of x, the first thing we do is change the f of x into a y. We then solve for x. So move all the pieces around to get x by itself. And then lastly, interchange all the x and y variables. So if it's an x variable, change it to y. If it's a y variable, change it to an x. And once we've done that, the resulting equation or the resulting function is f inverse of x. So when you get done doing this, you should not have y's in your equation anywhere. If you do, it's wrong because we can't have f inverse of x that has the y variable in it. It can only be x's. And then lastly, in terms of the relationship between base functions and inverse functions, the graphs. So the graph of f inverse of x So to find the graph of f inverse, we reflect f of x on the line y equals x. So on our graph, y equals x is what? It's this 45-degree line that cuts through the graph. So let's say that my f of x is square root of x. Well, we know that looks like what? It looks like this picture. So if I wanted the graph of f inverse, even without calculating it, I know it's what? Basically, if I took this piece of paper, folded it in half, wherever this line ends up, that's where the f inverse is. So in this case, it's actually going to be this picture here. This is f inverse. Without even calculating it and plotting points or doing any of that, I know that's what the graph of f inverse looks like because it's whatever is reflected across this line y equals x. All right, so that will do it. That is our content for inverse functions. Come on back and we will check out a bunch of examples of inverse problems.